Okay, the next class of functions we're going to talk about is logarithm functions or logarithmic functions, and these actually turn out to be the inverse of exponential functions. So let's talk about the definition of a logarithmic function, or we could just say log function. Okay, so a has to be greater than 0 and a can't be 1. Then this equation, y equal the log of x, and that's how you read this, y equals the log of x base a is the little number, is equivalent to the equation x equal a to the y. Okay, so actually it turns out that this log is really just another way to write an exponent. So the domain of the log function is actually positive real numbers. Now remember, that was the range of the exponential function, but now this is the domain of the log function. And the range of the log function is all real numbers. And if you'll remember, the domain of the exponential functions was all real numbers. Now, I found the best way to understand logs is to start with exponential equations that you know to be true and write them in log form. So let's talk about, okay, we know that 2 to the 4th power is equal to 16. Okay, well, this power 4 is what the log actually equals. The log actually equals this power. So you write the power or the exponent as what the log equals. And then you're going to have that equal to a log, and the base is going to be 2, which is the same as the base of this exponential expression. See, the base is 2. And then the argument here, 16, is what this exponential expression equals. So basically, if you read it the other way, it's actually easier if you read it the other way. For this statement here to be true, let me show you. For this statement here to be true, then the base 2 raised to the result 4 must equal this guy here, which we can call the argument 16. So as long as 2 to the 4 equals 16, this log is a true statement. Okay, now we can do that with some other examples. Let's say we have 3 to the negative 2 equals 1/9. Well, the exponent is what the log is going to equal. The base is going to be the same on both of these, so the base is going to be 3, and then 1/9 is this number here. And then if you read it the other way, you can say, okay, 3 to what power equals 1/9? Well, the answer is what? Negative 2 equals 1/9. Same thing up here. This answers a question, 2 to what power equals 16? Well, the answer is 4. Okay? So now let's do 6 to the 0 equals 1. We know that's a true statement. So 0 is the exponent. We have a log with a base 6 because that's the same base we had here, and 1 is going to be our argument. Now, this log answers the question 6 to what power equals 1. So what power what power do I raise 6 to get 1? Well, you know it's got to be 0. And then finally, I can give you a little more abstract example. I can say x to some m power equals 100. Well, m is what the log must equal. And then since over here the base is x, here the base would be x, and over here the 100 is going to be the argument. So this says x to what power equals 100. So I don't know the answer, so I'm just putting m there. X to what power equals 100. Now, it's actually, I find it easier to go the other way. If I give you a true logarithm equation, I find it easier to write it in exponential form. So this says 3 to the 4th power equals 81. And so those two statements are basically say the same thing. This says 2 to the negative 5th power equals 1/32, or 1/32. And the first two you can see are true. The second one you can't really decide whether it's true because you don't know what the variables are. But this says x to the z power equals r plus s. So that's how you write from log to exponential form. Now, the natural log function is actually denoted by y equals ln x. And y equals ln of x, it's understood that this has a base of e. So y can only equal the natural log of x if e to the y equals x. So this would be the same as saying e to the y equals x. Now, to graph this function, if you wanted to graph a log function, you actually can probably graph it better if you write it in exponential form. So let's say you wanted to graph y equals the log of x base 2. Well, you can write that in exponential form by just saying 2 to the y equals x, or x equal 2 to the y. Okay, so then it's easier to graph this by plugging in y values and then getting the corresponding x values. So for instance, if I plug in a y value of -2, well, we learned earlier that 2 to the -2 is 1/4. So I would get x equal 1/4. And if I plug a y value of -1, I get 2 to the -1, which is a half. And if I plug a y value of 0 in for y, for x, I get 2 to the 0 is 1. And then if y is 1, for x, 2 to the 1 is 2. And then if y is 2, 2 squared is 4. So if we were to graph these corresponding points, the point 1/4 for x, -2 for y would be about right here. And then the next point would be 1/2 for x, -1 for y, so that would be about right here. And then you would get the point 1, 0, and then you get the point 2, 1, and then you get the point 4, 2. So you can see that this graph starts down here, and so it goes down forever. Okay, so there's your -infinity for the range up to +infinity for the range. But notice the x values can't be 0, but they have to be numbers greater than 0. Now, if I wanted to graph y equal natural log of x, I'd write it as x equals e to the y, because the base of the natural log is e. So I'd have e to the y equals x. And so I could do the same thing for that. I could plug in y values and get the corresponding x values. So if y is -2, x would be e to the -2, which is about 0.14. If y is -1, x would be e to the -1, which is 0.37. If y is 0, x would be e to the 0, which is 1. If y is 1, x would be e to the 1, which is about 2.7. And if y is 2, x would be e squared, which is about 7.4. So I didn't plot the points here, but let's see. At -2, you're going to get a very small x value. And then for y, when y is -2, x is going to be very small. And then when y is -1, x is going to be a little bigger. And then when y is 0, x is going to be 1. And then when y is 1, x is going to be out here about 2.7. And then if you go up to y equal 2, you're going to be way out here over 7. So you can connect the dots and you get a graph that looks like that. So it looks very familiar, very similar to log of x base 2. Now go ahead and read this, but remember that functions that are inverses of one another, like this function is y equal 2 to the x, and then this function over here is y equal log of x base 2, and they're inverses of one another. And you might remember from algebra that when two functions are inverses of one another, they're actually mirror images across the line y equal x, which is this green line here. Now real quick, I want to just mention a common log. If you see a log written without a base, it's actually understood to have a base 10. So if you see just logx, it's actually a base 10 log, just like lnx is shorthand for a base e log. Now it would look very much like this up here, except it would actually flatten out a lot quicker. So that's really the only difference you'd have on a base 10 log. And you can, read the rest of this. Okay. And I gave you a few values for it there if you want to read them. Now, let's talk about the properties of logs. Well, the properties of logs, for all positive real numbers, we know that a cannot equal 1, and the log function has the following properties. The domain is the set of all positive real numbers. So if you go back up here, and remember this is the log function right here, so the domain is all positive real numbers, and the range is all real numbers. Okay, and the x-intercept is the point 1, 0, which is right here, and then has no y-intercept, and the y-axis is actually a vertical asymptote. So this y-axis is a vertical asymptote to this graph, and then the graph is actually increasing if the base is greater than 1, and decreasing if the base is less than 1. But so to give you an example of that, if your base was less than 1, the graph would actually look like this. Okay, it looked kind of like this. So basically you'd still have all the same properties, except it would be a decreasing graph. Okay, now these are the properties of logarithms. So let's run through them real quick. The log of a base a is always 1. So here's an example of that. If I want the log of 5 using the same base, I'm always going to get 1. The log of 1 is always 0 regardless of the base. So I could say the log of 1, regardless of what base I use, is going to be 0. The log of a to a power base a is just equal to the power. So if I want the log of 5 to the 7th using the same base as the exponent here, 5, see I have, for the exponential expression, the base is 5, and for the log the base is 5. So I would just get this power here, 7. And then the log of m times n, base a, is the log of m plus the log of n. So an example of how that would be used would be if I had the log of 2x base 3, that's the same as log of 2 base 3 plus log of x base 3. And for a quotient, it works as a difference. So if I have the log of m over n, that's going to be the log of m minus the log of n, using the same base. So the log of x over 4 base 2 would be the log of x base 2 minus the log of 4 base 2. Now these are just ways you can write them if you need to. And then if I have the log of m to the p base a, now notice this time this is not the same base as I have down here. Well, I can't eliminate it, but I can write this as p times the log of m base a. So if I have log of 7 to the 5th base 3, well, the 3 and the 7 don't match, so I can't just eliminate it, the log, but what I can do is say that's 5 times the log of 7 base 3. And then a couple of other properties. If 2 logs are equal, their arguments have to be equal. So if this log base 2 equals this log base 2, then the argument 2x minus 5 must equal 5x plus 2. And also if 2 arguments are equal, their logs have to be equal. So if I have 4 to the 2x equals 32, then I know the log of 4 to the 2x base 3 equals log of 32 base 3. Now I just chose base 3 randomly. Later we'll learn that we'll use particular bases to solve these. And then last, a to the log of p base a is just p. So if I have 3 raised to the log of 2x base 3, then that equals 2x. Okay, the last property is the change of base formula, and it shows that if you have the log of x base a, you can change it to any base you want, log of x base b over log of a base b. So you can pick whatever base you want, but the log of x has to be on top, the log of a has to be on bottom. So if I wanted the log of 235 base 7, I could actually use what's on my calculator, the common log of 235 divided by the common log of 7, or I could also use the natural log of 235 divided by the natural log of 7, and either one that I use will give me the same answer. To 3 decimals, it's going to be 2.806. And so in the next video, I'll do some examples of log properties and a couple of other problems.